Hello everyone, this video lecture has been created to serve as an out-of-class resource for a flipped classroom session in Fundamentals of Digital Logic Circuits. This course is being taught for second year B.Tech students at GITAM University, Hyderabad. In this lecture, we are going to review DeMorgan's theorem and its proof, DeMorgan's laws using logic gates, and application to digital logic circuits. DeMorgan's theorem is an important logic theorem for digital electronics, which is often used to simplify Boolean expressions with large inversion bars. The theorem says that inversion bar or a Boolean expression can be broken at any point provided the operation at that point is replaced with its dual, that is logical AND with OR and vice versa. This theorem is named after the 19th century British mathematician Augustus DeMorgan. DeMorgan's theorem brought out a pair of important laws for transforming logical expressions with long inversion bars into simpler ones. The first DeMorgan's law is stated as complement of A and B is equivalent to complement of A or complement of B. Similarly, the second DeMorgan's law is stated as complement of A or B is equivalent to complement of A and complement of B. So, in this example, the long bar or the complement of A and B is broken at this point and the corresponding AND operation is replaced with its dual, that is OR operation. We need to remember that DeMorgan's laws are very valid for Boolean expressions containing any number of variables. So these two examples show a typical 6 variable Boolean statements containing AND and OR operations. DeMorgan's theorem can be readily verified by perfect induction as well as by Venn diagrams. Since Boolean variables can take only two values, that is 0 and 1, perfect induction can be used to verify DeMorgan's theorem by substituting the variables with the zeros and ones, forming a truth table, and comparing left hand side and right hand side of the statement. So for example, a two variable DeMorgan's law stated as a complement of x and y is equivalent to complement of x or complement of y, we need to form a truth table for columns corresponding for left hand side of the DeMorgan's law and right hand side of the DeMorgan's law for all possible values. So because 0 and 1 are the only two possible values for any logical variable, Boolean variable, we can find that the values corresponding to the left hand side of the DeMorgan's law and right hand side of the same are equivalent, thereby serves as a proof for this statement. Another simple visual aid to verify DeMorgan's law is by Venn diagram. We know a Venn diagram contains elements like squares and circles, etc., to represent logical variables and their relations. Venn diagram provides for a more intuitive understanding of how the expressions on the left hand side and the right hand side may be equivalent. In this diagram, in universe, set containing 0 and 1 is represented by the square, variables x and y by the circles, and their intersection is by the common shaded area. The figure B is corresponding to the left hand side of the statement, and similarly the figure E corresponds to the right hand side of the statement. By comparing these two figures, we can readily say that this serves as a proof for DeMorgan's theorem. DeMorgan's laws describe the equivalence between gates with inverted inputs and gates with the inverted outputs. The diagram shows an AND gate with the inverted output is equivalent to an OR gate with the inverted inputs. We know that an AND gate with inverted output is nothing but an AND gate. So thereby an AND gate is shown as equivalent to an OR gate with the inverted inputs. Similarly, an OR gate with an inverted output is shown to be equivalent to an AND gate with inverted inputs. We also know that an OR gate with the inverted output is equivalent to an OR gate. So thereby it is equivalent to an AND gate with inverted inputs. DeMorgan's laws are useful in the implementation of the basic gate operations with the alternative gates, particularly with NAND and NOR gates, which are already available in IC form. So DeMorgan's equivalent gate symbols are shown in this diagram, which are very useful in converting digital circuits to contain either only NAND gates or only NOR gates. So here an AND gate is shown to be equivalent to an inverted input NOR gate, and an OR gate is equivalent to an inverted input NAND gate, and an AND gate is equivalent to an input inverted OR gate, and an OR gate is equivalent to an input inverted AND gate, and finally the NOT gate is equivalent to input inverted buffer. So these symbols find much use while applying DeMorgan's laws to practical digital circuits. Topics discussed in this lecture include DeMorgan's theorem, proof of DeMorgan's theorem, DeMorgan's laws using logic gates, and application of DeMorgan's laws. Thank you for watching.